Hello folks, welcome to this video where we're going to be discussing how to solve polynomial inequalities. So a polynomial inequality is kind of an extension of what we've already been discussing. We have been discussing already working with polynomials, but it's mainly been with equations. Now that we bring in the inequality idea, that simply means that we're going to have these less than, greater than, those kind of situations come up. So let's dive right in. So first of all, this problem, x squared minus 4x minus 5 less than 0. If this had been equal to 0, such as this, minus 4x minus 5 equal to 0, then we would have basically been trying to find what's known as the zeros of this polynomial or the functions, which we've learned is pretty much kind of like saying let's find the x-intercepts as long as they're real. So let's kind of just take a second and look at what that would look like. Since we have three terms we've been discussing previously, that there's basically two ways that you can solve this. There's others, but we've been focusing on two. One is you could look at factoring this, and if you factored this, you would have x and then 1 and 5, and it would look like this. So this would be the factored form. And then, as we've been discussing, the zeros would be what would make each group come out to be 0. Therefore, it would be x equals -1 and x equals a positive 5. So that's if we were working with equations. But now we're not. We're working with inequalities. So there's a lot of similarities in this, but just one real extension. Well, let's think about what this is going to look like. If I had a graph, then this is going to be a parabola that's going to open upwards because the number in front, the leading coefficient, is positive. We have x-intercepts at -1 and positive 5. So if I look at this on a graph, it's going to look something kind of like that. Now, this idea of being less than 0, what that essentially means is we're trying to figure out where this function, I want to know where the function is less than 0. Well, graphically what that means is where is the function being the red part that I have here, where is it less than 0? Well, less than 0, let's think about what that means over here on the graph for a second. Well, on the graph, less than 0 means where is it below the x-axis? Because in this equation, this is kind of like one equation over here on the left, and then this is like one equation over here on the right. And I'm looking at how these two compare to each other. So whenever I say where is the red part, the x squared minus 4x minus 5, where is it less than 0 at? Then graphically, I'm looking here and saying where is the red part below the x-axis? Now you can actually see that graphically here. It's below the x-axis from here to here. And that should make sense to you because when we find these x-intercepts, these are locations where the graph crosses the x-axis. So there's that one, and here's this one. So that represents kind of changing points, and we call these critical values. They are points to where we need to investigate further because something's changing. Critical points or critical values. Sorry, I was saying one thing and wrote another. Critical points or critical values at -1 and positive 5. So in this case, when we were looking at where is it below 0, the below 0 is the part that we've highlighted right here. So now if we were actually describing this and writing it out, then I would say that it is below 0. If I do this as an interval, it starts below 0 here, and then it goes back up here. So if you remember what those critical values were, the -1 and the positive 5, putting all this together, I could say that it is below 0. Remember, that was the question. Where is the function below 0? And I can now say that it is below 0 in the region from -1 to positive 5. I do not need a bracket on that. That should have been a parenthesis. So let's backtrack that. -1 to positive 5. In that region, which is symbolized by the part that I have highlighted here, it is below 0. Now, if, for instance, this had not been below 0, but rather had asked us where is the graph above 0. So that would have been indicated by a greater than. So it would have been something like this, greater than 0. And then I would still have that function over here. In that case, I would have been looking for the parts up here. So those regions would have been two different regions. I would have had this section, and then I would have this section. So the greater than 0 would have been on the left side, everything from negative infinity to -1, and then it was picked up and done the other one starting at 5 going to infinity. Okay, so that's how you do those polynomial inequalities. All right, so hopefully that wasn't too bad. Let's check out another one real quick. So I'm going to come over and look at this one. Now what you should notice about this one is that it's not equal to 0. There's like two equations. So when you're doing these kind of graphs or doing these kind of equations, there's two ways you can do it. One way is you could graph the left side, and then you could graph the right side and then compare that and see what it looked like on a graph. Another way that you could do this is to make it similar to the previous problem. We could move everything to one side. So if I was going to move everything to one side, I would come here and subtract x from both sides, and then I would subtract the 3 from both sides as well. And if I did that, my new equation would be x squared plus 2x minus 8 less than or equal to, everything here would cancel, 0. And now this problem becomes very similar to the last problem, and then you could work through it from there. Okay, and then it would basically be the same thing. So once again, if I was to factor this, that would be one way. That would be x, 2, and 4, and less than or equal to 0. My critical values, or my x-intercepts, would be x equal 2 and x equal -4. Again, thinking about what this is going to look like, I would have an x-intercept here at 2 and one over here at -4. The leading coefficient is positive, so again, I know this graph is going to do something like that. Once more, the question here is where is it less than 0? So again, I'm looking for this region here below the x-axis. And in that case, I could say this is a critical value of -4, 2, and it would be between -4 and 2. Now this time I'm going to put brackets, and the reason why is because I have the equal to. So I'm not only concerned about where is it below the x-axis, which is that imaginary line there. I'm not just concerned about where is it below, but also where is it equal to 0. And equal to 0 would actually include being on the x-axis, and that would happen at these two particular critical values. So that's why this time it's in brackets, and the previous time why we had it in parentheses. Now before we go away from the polynomial inequalities, I want to show you this one that we did first, how it looks if you look at it graphically. We chose to solve this kind of algebraically by factoring, but I could have done this graphically also, either by Desmos or using the calculator. So if I hop over to Desmos real quick, I already have this equation in. There's that parabola that we just talked about. And now if I put that y equals 0, you can see that show up here on the x-axis. So see it right in there. And the question was, once more, where is it below the x-axis? So if I'm looking at it graphically here on Desmos, my first challenge is to figure out my critical values. And that would be that point there and the point here, which we said just a moment ago. So there's my critical values. Now I just need to know when is it below, and it would be below in that region, just like we said before. Okay? All right, so that is polynomial inequalities. Now, second thing is what happens if we have what's called rational inequalities? Well, rational inequalities simply mean that we have a fraction. So it could look something like this. So let's see if we can get this up here. Rational inequalities. So we're still going to have those inequalities going on but this time we're going to have some fractions involved. So we could have a problem that looks something like this. Oh, let's do an inequality. Now, if you think about what rational inequalities look like, let's check that out graphically first. All right, so let's get over here. I have that in Desmos ready for me. Okay, so here's this function 3x divided by x plus 6. This is the graph. You see that we have some asymptotes going on here. Vertical asymptote that looks like at -6. If I zoom in there just so you can kind of see that. And then a horizontal asymptote that looks to be at about 3, which it should be based off of what we've discussed previously. So the question is similar to before. The question is, where is this function below 0, less than 0? So if I'm looking at this, the question, where is it below 0? Well, I've got my 0 equation in, and you can see that occurring right here. So that's what we have. So we would just have to describe that, where that's occurring at. All right, so how do we actually put this into numbers? How do we put it into an answer? Well, when you're doing these, it's similar to when we did the polynomial inequalities. We need to know what the critical values are first. That's what's going to kind of help us. So keep in mind that that kind of drives the show. What are our critical values? Well, the way you figure that out with rational inequalities, there's two parts. One is we need to figure out what causes issues in the denominator. In other words, those points of discontinuity, our vertical asymptotes, our holes, things of that sort. So in this case, what would cause a 0 in the denominator? What causes problems? If you look at that, in this instance, it would be x equals -6. That would be the issue. That's our problem with our domain. X cannot be -6. So that is one of my critical values. Okay, the other part is to figure out what would make this equation true if this was an equal sign. So in other words, I'm trying to figure out what would make 3x divided by x plus 6 equal to 0. So let's solve that. Okay, so one thing you can do here is treat it like a proportion. So if you're doing this as 0 divided by 1 cross multiply, you would have 3x, if you cross multiply it here, equals 0. And in that situation, divide by 3, and we would have x is equal to 0. So there's my other critical value. Now, looking at this where we were on the graph, -6 and 0. Well, let's see what's happening at these two situations. So if I'm going to come in here and put in x equals 6, and then I'm sorry, not x equals 6, it was x equals -6, and x equals 0. So let's see what happens if we do that. So I'm going to go x equal to -6. That's not showing for me. Give me 1 second here. There we go. I got them in. So now let me turn them on, and you can see how it kind of chops the graph up. Remember, the question is, where is this graph below 0? And that does seem to have kind of isolated it there into that region. So here's what the critical values do. The critical values, in a sense, simply divide up the x-axis or the number line into its different regions. So it gives me a division point or a critical value at 0. I have one over here at -6. And that gives me 3 regions based on this. Now, to know whether it's going to be less than 0, which basically means negative, in each region, we could plug a number in and check it. For example, if I try to think of a number that's over in this region, well, that could be 0.5, 1.7, 2, 3, 10, 100, 1,000, a million. But I want to pick an easy number. So the easiest number probably to pick is the number 1. If I plug the number 1 into this equation, let's see if it comes out positive or negative. Well, 3 times 1 would be a 3 on top, and on bottom, 1 plus 6 would be 7. So I'd have 3 over 7. Well, I really don't care about the number. I just want to know if it's positive or negative. In this case, it would be positive. So in this region over here to the right, it's going to become positive. I don't want that. I want to know when it's less than 0, when it's negative. So let's try this area here. At an easy number there would be -1. If I plug in -1, 3 times -1 would be a -3. And on bottom, a -1 plus 6 would be 5. Well, again, I don't care about the number. I want to focus on its negative. So, hey, that's what I want. That's negative. And just to make sure, let's check out this last region over here. An easy number, let's try -10. That I like even numbers. So on the left, or on the top, 3 times -10 would be -30. And then on the bottom, -10 plus 6 would be a -4. A negative divided by a negative is going to be positive. Okay, so you can see this is indeed the negative region, the part that's below 0. So the question is, when is it below 0? That was our whole question to begin with. Well, here's my interval. See, it's based on those critical values. It's everything from -6 to 0. So, where's it at? It would be from -6 to 0, using parentheses because we do not include the endpoints. Okay? All right, so let's do one final piece here. What happens when it's not equal to 0 like this, kind of like it was before with the polynomials? So let's see what we can figure out here. Okay, so I have x plus 1 divided by 2x minus 4 less than or equal to 1. Okay, so similar to before, I really need this to be less than or equal to 0. That would be helpful. I don't have to do that. There's some other ways, but it's definitely easier if we can get it equal to or less than or equal to 0. So let's see if we can go ahead and figure that out. All right, so to do that, I need to subtract 1 from both sides. And if we do that, then we're going to have x plus 1 divided by 2x minus 4 minus 1 is less than or equal to 0. Now, I cannot just subtract those. Remember, to subtract or add, you have to have common denominators. So in that case, I need to multiply this one by that common denominator, 2x minus 4 on top and bottom, so that it would match this one. If we do that, then the new equation here is going to be x plus 1 over 2x minus 4 minus 1 times 2x minus 4 over 2x minus 4. Well, the 1's really not doing anything, so I could kind of backtrack that and simplify this a little bit. 1 times anything is just that thing. So here we go, 2x minus 4 over 2x minus 4. Now let's see if we can clean that up a little bit. Well, x minus 2x would be a negative x. 1 minus a negative 4 is going to be 1 plus 4, or 5, all over 2x minus 4, less than or equal to 0. So there's the real question we're trying to figure out. Now this works really similar to the other problem we were just doing previously. So remember, the question, in order to do this, we need to know what the critical values are. That's the big question, because that'll kind of drive the show. So here we go. The way we do that is figure out, first of all, what would cause problems in the denominator. So what would make the denominator equal to 0? So let's figure that out. What's going to make that whole bottom come out to be 0? If I move this around, then I would have 2x is equal to 4 divided by 2, and we get x is equal to 2. So there's one of my critical values at x equal 2. Okay? Now, other part is we got to figure out what would make the whole thing equal to 0 as a whole. Now, if we solve this for what would make this equal to 0, then like before, we simply need to cross multiply as a proportion. So if I do this, I would have negative x plus 5 times 1, which is going to give me negative x plus 5. And then if I do the other way, 0 times that is simply going to be 0. So it's just a matter of solving this. And if I do that, subtract 5 from both sides, then I would have negative x is equal to negative 5, or positive x is equal to positive 5. So there is my other critical value. So now I can do like we did before. I have critical values at 2 and 5. And at this point, we just need to pick something from each region to test it out to see whether it's going to be positive or negative. So over here, let's pick out 0, because that's really easy. If I plug it into my equation, negative 0 is 0. 0 plus 5 is 5. And on bottom, 2 times 0 is 0. 0 minus 4 is a negative 4. So that's going to come out to be negative. Okay, well that's what I want. I want when it's less than or equal to 0. Now what about in this region? Maybe I pick 3. So negative 3 plus 5 is going to give me a 2 positive. On bottom, 2 times 3 is 6. 6 minus 4 is 2. Excuse me, 2 over 2, that comes out to be positive. And then on the right side, maybe 10. Negative 10 plus 5 is going to become a negative 5. 10 plugged in here times 2 would be 20. 20 minus 4 is going to be 16. Either case, it comes out to be negative. So the question was, when is it less than 0? Meaning, when is it below 0? When is it negative? And we can see that happens here in this region and here in this region. So let's state where that happens at. Well, it happens from negative infinity up to 2. Now I have the equal to here, so it can be on the x-axis. So that needs to be included, put together with starting over here at 5, going to infinity. And that is my solution. Now, if we look at this graphically, because we didn't look at the graph at all in this one, but if I look at this on the graph to kind of see how all this ties together, then let's see what happens. I have this. Here's my equation in purple. I've already got the 2 critical values there so you can see that. And remember, the question was, when is it below 0? When is it below the x-axis? And you can see that happening here in this region. There's that 2. And then there's the 5, and then it goes again in that region. So there's the 2 areas. So you have the algebraic approach, you have the graph approach. Either way works. That's how you do rational inequalities. So we talked about polynomial inequalities, we talked about rational inequalities, identifying the critical values, and that's all there is to it. Hopefully that helped. See ya.